Hi, good afternoon. I'm ShImell. I work for GurIt, Composite Engineering. We're part of the GurIt group that, as well as does engineering, sells composite materials. I'm here working with Haramain and Nurettin, my friend, who helps me in Turkey. He's sitting over there. Normally, I'm involved in marine engineering, so 20 years of engineering products in Turkey. But this time, I'm talking about other projects. As I say here, this is architectural, industrial, and I'm not trying to sell engineering, I'm just talking about interesting projects. Much more fun than selling something, okay? Why use FRP? People think it's normally a lightweight structure. My view is you shouldn't think about just lightweight. You should think about other advantages it gives you. Stiff or flexible, fire resistant. There are lots of different reasons to use composites, not just because they're lightweight, not just because they're expensive, but different reasons to do it. I'm going to show some examples of where composites could be used you wouldn't think they're normally used at all. This example is in England. The main problem is it's a big tidal river. When the tide was high, the lifeboat with an ordinary bridge couldn't get out of the river. So they had to have a bridge which is really shallow and had to open many times a day to let ships out. Each of those legs is 30 meters by 10 meters, and in steel we saved, it was 20 tons in steel. The composite, each leg was 6 tons. So if you look at the size of this ram, it's a really small ram, and it needs small amount of energy, small hydraulics to lift the gate every time. It's GurIt core materials, fire-resistant core materials, so it's carbon, a little bit of carbon, and mostly glass, and for passengers and for bicycles. It's a really good example of cost-effective materials, and actually the foundations are really small for what is a very big bridge spanning 60 meters. We've been doing a lot of mosque roofs. Why mosque roofs? They're a very hostile environment. They have to last many years without maintenance. But this one is a rotating roof. So all the mosque opens out to let sunlight in, and it has to run on ball bearings with a really light mechanism and no maintenance. So these roofs last for many, many years, and they completely open out with very small bearings. It's a really interesting use of composites in a very hostile environment. It's sunny, 50 degrees, hot, sand. Yes, that's hostile, it's not nice. Really interesting project. A really rich guy in Switzerland owned his house in a very small village, had a new roof on his building, supported by glass. The normal problem was, it's 24 meters by 7 meter roof. To make it in pieces and deliver the roof, he had to block the main road to the village for about 2-3 days. It was chaos. And we got asked to bid for this job, and we said, actually, instead of weighing 12 tons, 10 tons, we can make the roof in 2.5 tons with insulation, and then they could deliver the roof by helicopter to his building. So they made it in Holland, put it on a barge, shipped it to Basel within 20 miles, 30 kilometers from the roof. One helicopter picked it up and dropped his roof on his building. No problems with transportation. Interesting thing was, it rested on glass. The top surface was 70, 80 degrees centigrade. The bottom surface was 20 degrees centigrade, and it mustn't bend when it got hot. So we used carbon fiber and tuned the roof so it stayed completely flat and didn't bend in the heat. If it bent in the heat, the glass would have broken. But because it stayed flat, the glass didn't break at all. Use a really good video on YouTube of this being delivered by helicopter. It sounds good in theory, but the wind started to rotate the roof, which is not very good. Next interesting project. These were 2 bridges in England to span a railway line. Now, normally they're steel bridges because it's cheap. Now, why make them in composite? The cost of shutting down the railway line about 2,000 euros per 10 seconds to shut down a main railway line. The steel bridges were a day to shut down the railway line to install a steel bridge. A composite bridge was installed in 30 minutes. 30 minutes. So each span here is 12 meters. The bridge weighed 6 tons, or 4 to 6 tons, finished. Was picked up with one crane, dropped on foundations, and the foundations were surface foundations. So they weren't big structural foundations, we saved so much weight going. And now the whole of the British Network Rail is having composite pre-made bridges for the rail system. It saves them so much time and money. So it's not just lightweight, it's saving money and time. I don't know if you saw the release of the new Apple iPhone X, the Apple iPhone 8. It was done in a theater in California. In the theater is one big glass, 44-meter diameter theater with a roof on top. That roof is carbon fiber. And it's supported solely by the glass. This is the roof. 44 segments with all the insulation. And this is in a really earthquake zone. So a lot of earthquakes here, all supported by, I think it's a 5-meter glass wall. No supporting structure. A one-piece carbon roof dropped on top with all the insulation completely finished. And the deflection limitation was very small because of the glass requirements below. A single point lift in the middle. I can't show you many pictures of this because of confidentiality reasons. From the app, you have to show what Apple tell you show. This is the reception areas. These reception areas are supported on, they are 40 meters long. They're supported in a line on a row of pillars. At the ends, they're supported by glass all around, but the glass couldn't be strong enough to take the weight. So they have 2 wires at each end, and these are that is a tension wire there. They pull the roof is made with a bend. The wires pull the roof flat, and so no matter what comes on top, the roof never sags down, and the glass doesn't take any load. So the glass is freestanding, not supporting the roof at all. All it's supported is 4 pillars in the middle, take the whole weight of the roof. The wires take tension load, and the wire is hidden inside the glass, so it's completely invisible. Really interesting use of composites. But Apple has got a lot of money, so it's a more industrial use of composites. Top right-hand corner is the first crane we designed for Atlas. It's a crane manufacturer in England. You see these a lot of boats worldwide. The top right-hand crane, total composite weight 15 kilos. It carries 500 kilos. It is made just in one-shot carbon fiber product. So it's 2 female molds, carbon inside with a bag that they inflate, and the shape was designed by FEA. So our client came up with an angle, and we redesigned the shape so it had no webs required, no stability at all. It was fully self-supporting. They can make it really quickly, efficiently, at a low cost. Owners pick up the crane, put them in the deck, and lift up dinghies and tenders. The biggest one now is 1.2 tons of lift from a simple crane. The next stage is on the right, whoops. On the left, this is a David crane. It's lifting 5 tons. So 2 of these lift a 10-ton rescue tender. Total weight of the composite is 280 kilos. Inside is the winch. So the winch is integral. And that is the first one made. It was made 2 months ago, and they're testing it this week. The test weight is 25 tons test weight on 280 kilos of composite. And they tested up to angles 10 degrees both ways, so the whole thing is designed to work in a seaway. The next crane is started production here. This is a extending crane for a ship. At 10 meters, it's lifting a 3.5-ton Land Rover. At 20 meters, it's lifting a 1-ton payload for loading onto a ship. And this has started production already for a Fed ship yacht. They had to do composites. The steel Wayne cranes were so heavy, it affected the stability of the ship. And by doing composites, the the boat met all the stability requirements for class. These are the two davits when they're finished. The original steel davits on the top left-hand corner, that's how complicated they look with lots of winches and metal winches. This uses synthetic rope winch, and the winch is integral within the davit. So we designed the composites and the winch together. Why I use composites is not just lightweight, it's also they're flexible and fatigue resistant. Interesting use of composites we do as a wind wand. This is designed like a grass blade. Grass blade, when the wind blows, it goes flat. It goes flat, it loses stresses. It doesn't bend as much because the weight of the grass pulls the tip down and sheds load. The composites was designed the same way. So it's designed to flex. And on these, the wind pulls it down, these tips go completely level in strong wind and doesn't break. If you made it stiffer, it would stand up and the base would break. This one is 30 meters high and the tip will bend 17 meters in a breeze, but without breaking because the shape means it doesn't break. Really interesting use of composites. Doesn't necessarily mean carbon or stiff. They can be very flexible and high fatigue. Not just lightweight, low maintenance, formable, any shape you want and any color you want. This is bridges we did in Lisbon many years ago. They're spanning about 24 meters. The original metal bridges were designed for the Expo show, were big foundations. Took a lot of work, shows the motorway down. These are surface foundations. Each bridge weighed 6.8 tons. They came for a lorry, they dropped on the foundations, and the lorry drove off. And they're still there now. There's no maintenance, no painting required. The best bit was a lorry with a crane on drove into one of these bridges. Now, if it's a concrete bridge, it would be a disaster. People got killed. It would be a nightmare. Motorway was closed. The bridge got knocked off its foundations, landed on the motorway. Nobody was hurt. About a week of repair, they lifted the bridge back onto the foundations. The bridge is carrying on being used. Whereas with a steel bridge, people would have been killed. It would have been a big disaster. But this is still working fine. It was only designed 1998, and they're still fine, no problems at all, no maintenance, no painting required. This is the underground in London. It's a complete walkway covered by a one-piece composite moulding. It was built in 3 sections with all the wiring, the systems involved, fully finished, painted, and dropped on site. As you see, it's supported just by glass, very lightweight, and met all the fire requirements for an underground rail system, which is a very hard job to do. They're all GurIt cores, GurIt materials, to make this product made in England, but fully finished and completed and lifted on site. In any other materials, you couldn't do the shape. Really interesting, wacky project. An architect said they got treacle, and they created a beader treacle for spoon, and they turned it upside down. They said, can we have that in composites? It's nearly 30 meters high. At the top, it's 25 millimeter diameter, all in carbon, sits in the middle of a building. You can't see the top when taking a picture, it's so fine. Really clever use of composites. This is the Big Blue in London. It's the first example of composites supported by glass. We save so much weight. The skylight is supported by glass above a supermarket, and this sits on top like a flying saucer. It had to be really light, not an earthquake zone, but the quality of finish is fantastic. It still looks brilliant. It's a painted epoxy finish, and that really kept its light. The problem was the shape wasn't weight. Actually, the shape gave lift. So the wind hit the flying saucer, that actually took off rather than put weight on. This is sitting here still. It's quite an interesting project. Less supporting structure. This is something is quite interesting in composites because you can really make some big changes and big savings on steel. This is inside a tent for the Millennium. They made a 30-meter dome. Now, it looks quite simple. Each of those segments were made on the Isle of Wight. Each of those segments is maximum 5mm single skin. So they're 15 meters long, with just 2 stiffeners each side. By themselves, are very, very flexible. When they're bolted together, they're very light, and the walls, each of those walls is 2.4 meters, and they're only 5mm single skin. You can push them, and they wobble like a jelly. In the middle, they put a 300-kilo crane, 300-kilo camera in the middle, a 360 camera. The weight of the whole camera pulled the roof down and created a tension around the outside. And when the crane was fitted, the whole thing came really, really stable. And it lasted for 2 years as a show. Now we understand somebody's brought it, and it's outside of somebody's house. So you put a tie rod in the middle, got rid of the camera, and it's now somebody's house, and they live in it as a complete monocoque single-skin laminate. Carbon fibre house in Switzerland. Very rich guy wanted his bedroom as a monocoque carbon fibre sandwich structure just supported by pillars. Nothing else at all. It's an unusual way of use of composites, but it's really clever, lightweight use of composites. This was an interesting project. In New York, Whitestone Bronx Bridge, a very famous bridge, they didn't do maintenance for 15 years, and the wires started losing strength. They saw them, they started failing, basically. They realized they had a problem. They had to save weight. The problem was, I don't know if you've seen the Tacoma Narrow Suspension Bridge. This one, the same bridge method was used for this bridge as the one in New York. What they had to do, if you go backwards, and again. There was 6,000 tons of steel and damping underneath. They had to chop 6,000 tons off. So to do this, they had to put a fairing on the outside to make it aerodynamic. 20,000 square meters of fairing to make the bridge aerodynamic, and that sounds easy. In the winter, ice attaches to the cables. Each ice, so when the wind hits the ice, 20-kilo lumps of ice fall from 200 feet and land on the fairing. So this fairing had to survive 20 years, had ice landing on it, wind landing on it, bolted to the bridge without shutting the bridge down. It's an interesting composite solution. And this is the fairings being fitted. I was there. It was an interesting place while the road is still running. They fitted the fairings. They couldn't shut the road down. Very interesting use of composites in a very hostile environment. This is the clock tower in Mecca, a gift to the king. I'm not allowed to go there, but we did the engineering. This is 680 meters high. The cladding at the top is 28,000 square meters of composites. The clock tower is 44-meter diameter. You can see it from 100 kilometers away. Each hand is 23 meters, and they're full carbon prepreg arm, because if you made them from normal materials, the clock mechanism would be so big, it couldn't turn it. The weight, self-weight was so big. So the clock tower and the clock hands, everything is composite. I think there are 4 billion LED lights on this. At night, the whole tower lights up, and you can see it from away. To give you an idea of size, you see at the top, there's an apartment up there. There's a 3-story, that's all carbon fibre at the top. There's a 3-story apartment up there with a bedroom, a lounge, and a cinema. Up at the top. Up at the very top, yes. There's a 3-story apartment in the top of that. You can rent it, I think. I think you could rent. No, I think you can go up there. But I'm not quite sure who lives there. But there is an apartment on the top with a cinema. And it's all that's carbon at the top. And you're 680 meters up in the sky. No, we do the engineering. PCT beat this. We did all the engineering. So we do composite engineering. GurIt material, GurIt supply the materials. PCT in UAE, they built all the products there. Did a fantastic job. It was a really hard job to do. The reason they did more and more composites is, if I go back one, backwards. They designed all the foundations to here before they designed the top. And the bridge, the clock got taller and taller and taller as they designed more and more. So the weight couldn't go bigger and bigger. So they had, as the designers went bigger and bigger and taller, they had to save weight, otherwise it wouldn't work. It's fire resistance. People don't think of composites as fire resistant. We worked after the North Sea offshore. We did lots of fireproof panels. These panels were designed for a jet test, 1,200 degrees, for 60 minutes without the backside burning, for fire protection for the rescue offshore platform. All in composite panels. There's no way you could do it in metal. Now, all the composite panels in the offshore industry are all composites. Really interesting use of composites. Getting towards the end, for long life, PCT also made in 1998 mosque roofs. These are epoxy carbon, covered in ceramic tiles with epoxy. All the polyester roofs now, they've had 2 levels of paint to keep them, maintain them. This is now 20 years old. They come to look at it, it's exactly the same as it was before. No maintenance required, all covered ceramic tiles, no expansion, no correction, no change. They're a fantastic example of composites lasting a long time in what is a very nasty, hot, hostile environment. Where are we now? Normally finished. This is an interesting project. This is an architectural project in the middle of New Zealand, in the middle of nowhere, sitting on poles, but it really sees really high winds. Very interesting shape. It's a celebration area in New Zealand of a composite, multifaceted component, but it's quite big. It's 15 meters by 20 meters, sitting on poles. So this was a very interesting use of composites for architecture. The safety screens, these are in New Zealand. We made one. They fitted all you have to protect from people throwing instruments, throwing things on trains. They have wiring down there so people can't jump on and land on the track. They're made to be bolted to original bridges, so they can't be too heavy. We made one. There's now 1,500 of these of different colours all over New Zealand to protect all the trains. The last one, the Haramain roof station in Saudi Arabia. This is, the whole roof is composite. 44,000 square meters of roof, and there are per train station, there are 4 train stations. Each panel is 9 meters by 3 meters. Finished composite weight, 50 kilos a square meter, including headlining. They're all GurIt fire-resistant materials. There's headlining, lights, attachments. They're all made by PCT and lifted in sight. So there's wine composites, changing shape. So 28 different molded components over the 44,000 square meters. And they can all be lifted on site and pre-installed and pre-made to fit the roof. It's a fantastic example of composites being used for innovative architecture to give a very interesting structure. There's now all 4 train stations are finished. The quantity of materials is vast, the complexity is vast. Each mold, machine mold, made with Ampeg 22 resin, fire-resistant skins, fire-resistant core, and designed to live in Saudi Arabia, a very hostile environment, and these have been very successful. Well, I hope that's inspired you to think differently about composites. Try different areas. What you think might be steel or concrete, actually composites can give a good solution a lot of the time.
Thank you.
No problem. Okay, that's all. Thank you.